Hi, this is Team MiddayRingmall, and Matt and I are presenting to you our MAE152 project report, improving the structural integrity and lifespan of the acoustic guitar.
The goal of these modal analysis is to validate the first harmonic of each string matches with standard tuning frequencies. A simple cylinder is made with one end fixed and the other end free to move only in the axial direction. A tension load is applied to this end. The model is meshed with solids. Because an external load exists, we are required to use the direct sparse solver. The E string correctly shows a frequency for standard E as its first harmonic. Static analysis to ensure that the modifications would not result in yield or failure by the specified tension of the closed form solutions. For the modal analysis, we compared the error in frequency. The first harmonic for the low E string is supposed to be 82.4 Hz, whereas the SolidWorks solution produced 86.3 Hz, 4.73% from what is desired. For the static analysis, the closed form solution is a simple force over area relation, which, compared to the SolidWorks solution, gives an error of about 10.1%.
The guitar body can be construed as a simply supported system, where one fixed boundary is placed at the neck of the guitar, while the applied load with the sliding boundary is placed at the bottom of the guitar. Here we ran stress analyses on the guitar body. We replaced the strings with applied loadings where the tensions would be so that the mesh would not be too overfine and conflict. For a body shell of 3 mm, we observed that the guitar experiences a yield below its maximum stress.
A fatigue analysis sees the lifespan of each string. Because of each materials and their SN curves, all the strings would experience almost infinite lifetimes. Taking the D string using an SN curve for similar bronze tin alloy, 1.6 million cycles before failure. If a cycle represents each time the D string is played and assuming the string goes through 200 cycles a day, this would lead to a lifespan of about 22.3 years.
For our first design iteration, we scaled the guitar to be more convenient for the traveling guitarist, and then we ran modal analyses to confirm that the frequencies of the strings stayed consistent with that of the standard guitar tuning. Later we observed that the stresses endured by the D and G strings were above yield strength, so we had to run static analyses to improve the structural integrity of the strings and thus the lifespan of the entire guitar. Here are the results of thickening the shell and rerunning the analyses. We see that thickening the shell to 3.10 mm did help with the stress, but the max stress was still too large and overcame the yield strength of the material. But when thickening the shell of the guitar body to 3.30 mm, we observed that the maximum stress experienced by the body is 43.6 megapascals, which is less than the sigma yield and therefore able to withstand the high stress.
The third design iteration is to solve the problem of the D and G strings yielding by reducing their maximum von Mises stresses. For the D string, this consisted of reducing its area. For the G string, we needed to reduce the area and change the material from phosphorus bronze to alloy steel. The minimum factor of safety increased from 0.8 to 3.2. The final guitar product will have a modified wall body thickness of 3.3 mm and guitar string lengths of 376 mm and a full guitar length of about 548 mm. This table describes the properties of the guitar strings after the modifications. It should also be noted that we need to consider qualitative factors to better optimize the design, such as sound quality and comfort. Although these factors would lead to a better analysis and better final design, they'd be difficult to quantify and it is beyond the scope of the project. Thank you for your time, and thank you for watching and listening to our presentation.